Good.
Okay, so let me try again. So welcome everybody. I'm delighted to have Krishan Sabnani with us today, albeit virtually. Krishan is a networking researcher that made many seminal contributions to internet infrastructure design, protocol design, and wireless networks. He was vice president of networking research at Bell Labs from 2000 to 2013. And in that role, he managed all networking research at Bell Labs, and comprising 9 departments in 7 countries, including US, France, Germany, Ireland, India, Belgium, and South Korea. Krishan is a member of the National Academy of Engineering. He has won many awards, such as the IEEE Sumner Award and the IEEE McDowell Award. He's a fellow of the IEEE and ACM, and also a Bell Labs fellow. He was inducted into the New Jersey Inventors Hall of Fame in 2014. Other than that official bio, he's also on our advisory board for many years. And what greater endorsement to our department than his son, Kirk, who finished our BS and Masters in Security Informatics here in our program. So I know him for the last 6 years or so, but we have here our Tony Dabura, who knows him for I just learned 40 years working with him at Bell Labs. So to you, Krishan.
So here, thanks for this wonderful introduction. As J.R. mentioned, I've had a close association with this department for a long time. I've served for nearly a decade on the advisory board. And also more recently, I've been a visiting scientist in Juicy. So let me share my charts first. Just give me a minute. Can you see my charts?
Yes.
Okay, good.
Yes.
Good. So before I talk about major projects I've worked on, I want to just show you what the field I've been working in, and Jer and others have also been working in this field also. So what this field has done for the society. It has created internet. By the way, many of you are very young and just seen internet. Networking has gone through many cycles, and I can give a talk on the history of networking, but that's not what I'm going to do. But this is what you can do on internet in just 1 minute. 1.5 million gigabytes get transferred. And all sorts of apps are running on internet. I'm sure all of you have used these. Millions of searches are being done every minute. Millions of messages are being exchanged. Tens of thousands of folks are watching video. In fact, more than half the traffic on internet today is video traffic. Mobile traffic has been the fastest growing part of this traffic. From 2012 to 2017, this traffic grew by a factor of 13. There are just too many endpoints connected to internet today, and they're growing fast. There are more endpoints on internet than a number of people. And this traffic keeps on doubling every 2 years, and more apps are being added. So I started working on networking during my doctoral thesis at Columbia University. Then I joined Bell Labs. Then in '93, I started a wireless networking department. In 2000, I took over responsibility for entire networking research at Bell Labs. This was a highly talented research organization. There were 9 departments based in the US, France, Germany, Ireland, and India. There was also a small department in South Korea, which I've not shown here, but there was that department also. And here, thanks for reminding me about that. Then in 2013, I reduced my role at Bell Labs from management point of view, and it took on a smaller organization that was working on cloud computing for telecom networks. Then in 2017, I reduced my role at Bell Labs considerably, and currently I'm an ambassador at large and a consultant at Bell Labs. In fact, I officially retired from Bell Labs at the end of 2016 and didn't want to lose me. So they gave me a lifetime title of ambassador at large. And I still have a wonderful office in Murray Hill, New Jersey. Currently, I'm also advisor at some startups. I'm also participating in some DARPA projects at a company that came from Bell Labs, LGS, which is a part of a larger company, CACI. I've been teaching a course at Columbia University for the last 10 years. Krishan Sabnani and I started a company to provide e-learning services in remote parts of India. This company is called Edge Media. In these remote parts, internet connectivity is very poor. This company is still in stealth mode, so I'm not really spending any time talking about it. So here is a photo of Bell Labs in Murray Hill, New Jersey. This is a famous building where transistor was invented. Claude Shannon put together his information theory, and Unix and C were developed also in this building. So the most prominent piece of work I've done is soft router, which has become a foundation of software-defined networking technology, SDN technology. I'm sure all of you have heard about it. I'll spend a large part of this presentation on that topic. I spent a large part of my professional career working on networking protocols. This work can be divided in 2 buckets. The first bucket is my work on formal methods. This includes my work with Tony DeGour on conformance testing. Also worked on verifying correctness of protocols and converting between different protocol standards. Also synthesized a number of new protocols. For example, one of these protocols for reliable multicasting. Multicasting means sending information from one sender to multiple receivers. Also synthesize a transport layer protocol, which reduces control complexity using periodic state exchange. Also synthesized a protocol for wireless networks called AirMail. I've developed a number of product ideas which have generated large businesses. I'll give you 2 samples of them. The first one is my work on global roaming. This allows roaming between different types of cellular networks. This has generated a large business for the company I worked for, several $100 million per year. I've also identified a new class of denial of service attacks that can be launched against cellular networks and found ways of mitigating them. This has resulted in a product which has a lifetime revenue of over $150 million. I'm fortunate to get many recognitions. Here mentioned many of them. For my work on soft router, I was inducted into National Academy of Engineering earlier this year. For my work on protocols, I received 2 major IEEE awards, IEEE Sumner Award and IEEE McDowell Award. I became a Bell Labs Fellow and a Fellow of ACM and IEEE. Also won 2 significant Best Paper Awards, one of them from IEEE Abraham Prize Paper Award, then recognition as a Best Paper at ACM SIGCOMM in '89. I guess all of you know SIGCOMM is the most important networking conference. I've been granted a large number of patents which have generated large businesses. For these patents, I was inducted into New Jersey Inventors Hall of Fame and also won 3 Edison Patent Awards. This award is given to a patent which has had most business impact in the state of New Jersey. First, I'll talk about my work on soft router. By the way, I will encourage you to stop me if you have any questions, because this is a virtual session. I cannot really see how many of where my message is getting through. So when internet started, its underlying protocol was very simple. Best effort datagram protocol, but with time, complexity has been added to it. Internet is built using routers. Each router does both packet forwarding and control processing in a single box. Now, it's very difficult to introduce new network features. I remember a discussion with some folks from BT in 2003. BT, by the way, is the British telecom company. The folks there were complaining they could create new web applications overnight, but it took them forever to create new network features. So we have solved this problem by opening up these routers. Packet forwarding we do in hardware elements called packet forwarding elements, and control plane processing is consolidated in a few software servers called control element servers. This architecture makes it very easy to introduce new network features. This enhanced programmability is a key part of current SDN networks, software-defined networks. This has become a key part of many new networks. For example, networks being deployed by Google and Facebook are software-defined. Telecom companies are usually slow in adopting new ideas, but even they have adopted it in 5G networks. Now, the company I was working for at that time started an internal venture. This venture developed a product, 9980 AINP. This product has been deployed widely. For example, it's been deployed in Verizon's network. This invention of soft router was recognized as one of the most important inventions from the state of New Jersey. One other invention in this list was transistor. Now, on the right-hand side here, you see a model for internet. At the top, you see different applications: email, World Wide Web, phone traffic. At the bottom, you see many different communication channels: copper wire, fiber, radio. Traffic from all of these applications go over these different communication channels using a very simple protocol, IP protocol. But with time, complexity has been added to it. For example, support from multicasting, mobility, and VPN. There's a standards group, ITF, which defines internet protocols. They generate several hundred documents every year. Many of these documents need to be implemented in every single router. This makes control software very complex. This architecture also makes it very difficult to achieve network-wide objectives. For example, if you want to ensure a certain amount of traffic between two endpoints, that's very difficult to do. By the way, this is called traffic engineering. Now, if one or more routers are misconfigured, this can bring down entire networks. In fact, this has happened in some major North American networks. On the left-hand side here, you see a conventional router. At the bottom, you see packet forwarding. At the top, you see control processing. They're in a single box connected using a proprietary API. On the right-hand side, you see soft router model. At the bottom, you see packet forwarding elements. They are mostly hardware elements. At the top, you see software servers, control element servers. This does control processing. Best example of control processing is route computations. And evaluated functions such as virtual private networking is done in feature servers. Now, these software servers are connected to these hardware packet forwarding elements using a standard protocol. What this means is different companies can produce these different elements, and this makes introducing new network features very easy. The protocol we use was ATF's Forces protocol. Industry is another is using another protocol called OpenFlow. On the left-hand side here, you see a traditional router network. There are a bunch of these routers connected together. On the right-hand side, you see soft router network. There are a bunch of these packet forwarding elements distributed throughout the network, and then few of these control element servers. Each control element server supports multiple packet forwarding elements. Each packet forwarding element is bound to more than one control element. So even if one of these control element server fails, packet forwarding elements keeps on functioning. The last chart where I showed you that in current routers, packet forwarding and control plane processing is done in the same box. So the part that does control plane processing, it fails, it brings down the entire router. And we have eliminated that problem in this soft router architecture. This, by the way, increases reliability substantially. Now, one of the major benefits of this soft router network is it can be built at very low price points. For example, these packet forwarding elements can be built using commoditized silicon from companies like Broadcom. Also, it's very easy to manage a network like this because you are managing only a small number of control elements. Now, this reduces operational expenses. By the way, in the current network, operational expenses are significantly more than capital expenses. Managing current complex router networks cost a lot more money. Already explained, it's very easy to create new network features. Now, every year we are adding more and more control processing in these control element servers. We need more and more powerful servers. And that can easily be done in our architecture. It's very difficult to do in current routers. Now, we can also build these soft router networks at a very high reliability level. Forwarding elements, since they're mostly hardware, they're already highly reliable. And these control element servers can be made to be highly reliable by using reliability enhancing mechanisms, which are used in computing industry, such as failover and overload control. Now, there are a lot of different types of attacks that can be launched. Security attacks can be launched against IP networks. We can defend against these attacks in soft router architecture by adding perimeter defense mechanisms in these control elements. Examples of these are firewalls and intrusion detection software. Next, I'm going to show you some concrete benefits of this soft router architecture. Many of you probably have heard about OSPF. OSPF is a routing protocol used in internet. It computes shortest paths using Dijkstra shortest path algorithm. Each router has to run an instance of OSPF. That means it is doing these route computations separately. That means they can come up with different routing tables. This can cause loops in the network. So there are mechanisms to make sure that these views converge at some point, but this ends up taking a lot of time. Now, in our soft router architecture, we do OSPF computation in control elements. Each control element is doing this computation for many forwarding elements. So that means there's no convergence problem in the views of these forwarding elements. And also, we have very few control elements, and converging their views is very, very fast. Here is a simulation for an N-node network. And the event we are modeling here is the single link failure. In the graph here, on the x-axis is the number of nodes. This goes from 0 to 100. And the y-axis is the recovery time, which goes from 0 to 2.5 seconds. The top line is for a traditional router network. The recovery time goes from 1.3 seconds to 2.3 seconds. For soft router network with one control element, the recovery time is only about half a second. And with 2 control elements, it's only about 1 second. So one of the things to notice here is there is a substantial increase in recovery time as we increase the number of nodes. Now, there is a similar benefit for another routing protocol that's used widely in internet called BGP. BGP is used for inter-domain routing. It again has a convergence problem. To deal with this convergence problem, what is done is these route computations are done in a few places called route reflectors. Now we're going to do this BGP computation in control elements, and we're also going to form a full mesh. This will minimize this convergence problem. Full mesh means that each control element can talk to every other element. Now we also worked on a network design problem. This is precursor to current SDN controller placement problem research community is working on. Here on the right-hand side, you see a bunch of these forwarding elements distributed throughout the network. Then we have a few control elements. We want to place these control elements in this C. We want to do it in such a way so that the load is balanced across all of these control elements, and we minimize distance between each forwarding elements and its associated control element. So this is similar to a K-way equipartition problem. We want to divide this graph into clusters of equal sizes. And for this, we use recursive graph bisection algorithm. There are many of heuristic algorithms available for this. For example, one of them is from Kernighan and Lin. We applied this to a 20-node ISP topology. And the right-hand side in the table, you see the results for that. The top row is for 2 control elements. So each control element has to support 20/2 forwarding elements, and average distance of forwarding elements from associated control element is 2.25. Other extreme at the bottom, when the number of control elements is 7, average load is 2.8 second. Forwarding elements, and average distance is 1.64 hops. Now, this idea of control plane disaggregation is a part of control SDN networks. This is, as I already mentioned, deployed widely by web players, and service providers like Verizon, AT&T also deploying it in 5G networks. I just want to mention here, software-defined approach is becoming very widely used. For example, you look at self-driving cars. They have a computer, electric motor, and a battery. These self-driving cars have a large amount of code. In fact, something like over 100 million lines of code, especially in the high-end models. So these are really, I would say, most complex software-defined pieces of equipment. Now, the lower layers of these wireless networks are also being implemented using this software-defined approach. Even in security, you know, I'm sure many of you heard about, especially people like here and Avi, of these zero trust networks. You heard about this term, software-defined parameters. In fact, I'll mention that later in this talk. Before I move to the next topic, I just want to stop here and ask you if you have any questions here. No questions? Okay. Next, I'll talk about my work on conformance testing I did with Tony Dabura. Conformance testing means checking if a protocol implementation matches its specification. The specifications are typically given in natural language. So what testers do is they take this natural language specification, which is a long document. For each section, they write a test. Now, the problem with this approach is these tests are very long, they are not even complete. So Tony and I decided to use formal methods to solve this problem. We model protocol as a finite state machine. This FSM stands for finite state machines. So finite state machine model is typically a directed graph. The nodes in this directed graph are states, edges are state transitions. Each edge has a label which has two parts, input and output. Input causes the state transition, output is what you will observe. So on the right-hand side here, which is unfortunately very small, I'll be distributing these charts, so you probably will be able to look at probably in more detail. This is a finite state machine for a simple protocol called alternating bit protocol. Now we want to cover each edge in this graph. After covering each edge, to make sure that the implementation ends up in the right state, we use unique input-output sequence. By the way, this is a term Tony and I coined. This is a unique signature for this tail state. For most states, these UIO sequences exist and are very short. To find an optimal tour through this graph, we use either Chinese postman or rural Chinese postman algorithm. We use Chinese postman algorithm if we can observe the internal state of the implementation. Now this results in a complete test and reduces, in fact, reduced testing time from weeks to a few hours. This work resonated very well in the research community. There were hundreds of follow-up papers and many follow-up doctoral theses. And the term Tony and I coined, UIO sequence, became a well-accepted term. We saw terms like partial UIOs and multiple UIOs. It also had a tremendous impact on practice also. For example, AT&T used this approach to test all of its switches and terminals for protocols used in those days, ISDN and ATM. And there was also a tool that was developed to generate test sequences. Now, this work is still used. Now here is a finite state machine with 7 states. 0 is the initial state. This is a double circle around it. Each has a label. For example, label from 0 to 1 is A/B. A is the input and B is the output. On the right-hand side, in the table, you see UIO sequence for each of the states. For example, UIO sequence for 0 is A/B, C/D. At the bottom, you see a UIO sequence for 6. It is A/F, C/D. Now, in 0 or 6, if you apply A, in 0, you'll observe B. In 6, you'll observe F. On the right-hand side, the bottom, you see a test sequence. This is basically we're covering each state transition, each edge. After covering each edge, we check whether the implementation is the right ending state using UIO sequence. We do some optimization to get this final test sequence. Now, I've also synthesized a number of new protocols. I'll give you a couple of examples. The first one is a reliable multicast transfer protocol. Reliable means you're sending information correctly from sender to multiple receivers. So multicasting again is sending information from one sender to multiple receivers. Transfer protocol, this is a protocol at the same level as TCP. The problem with reliable multicasting is sender has to deal with a large number of acknowledgements. each time one of the receivers receives a data packet, it has to send an acknowledgement back to sender. So suppose we have 1,000 receivers, sender will have to deal with 1,000 acknowledgements for each data packet it sends. So we solve this problem by creating a receiver hierarchy. So for each region, we pick a designated receiver, which combines acts from that area, and then sends this combined act back to sender. So this act implosion problem, we solved using this combining of acknowledgements. This work resonated very well in research community. There were a lot of follow papers to this, a lot of follow work. It also had a lot of impact on practice also. For example, AT&T deployed it in its billing network. So in this billing network, there are a bunch of these switches which were sending call detail records to some billers. Now, since it's billing information, high reliability is really important. For this reason, this was also used in financial industry. Also worked on a very interesting protocol. This is periodic state exchange transport protocol. This reduces control complexity using periodic state exchange. Now, if you look at a conventional protocol, what it does is each side, when there's a change in state, it sends this change in state to the other side. If this delta of state gets lost, then there's a recovery procedure, then recovery procedure on top of that. So these protocols become very complex. So in our design, what we did was we sent complete state from one side to the other side. We did this in both directions, and we did this periodically and frequently. So even if one of these state updates gets lost, no recovery procedure is needed because a new update will be coming soon. Now, this idea was received very well in the research community. Our journal paper won IEEE a Brand Prize Paper Award. Our conference paper was rated as the best paper at ACM SIGCOMM. This idea of periodic state exchange also became a part of an international standard called SSCOP, which was deployed in thousands of ATM networks around the world. Any questions? Next, I'm going to talk about some product ideas I worked on. The first one is global roaming. So when cellular networks were beginning to be deployed, there were many different standards, different types of these cellular networks. For a network based on one of these standards, there will be a database which will store user profiles, and there will be a unique authentication procedure for this network. So when a user wanted to move from one of these networks to a network of different kind, it had to go through a protocol converter. So if they would say in different types of these cellular networks, there were n different types of these databases, n squared protocol converters were needed. So we solved this problem by building a new network element called Super Distributed Home Location Register, Super DHLR. This has only a single type of database. In this database profile is a superset of a profile in each one of these different networks. And we also combine authentication procedures in this. Now, with this approach, only one type of database is needed, and n a very simple protocol data adapters will be needed. And just remember is the different types of these cellular networks. This resulted in a highly successful product. This has been deployed in 15 networks with over 600 million users. This includes Verizon and Sprint. So you may have used our Super DHLR. By the way, most of the industry is using this approach now. Now, also identified a new class of denial of service attacks that can be launched against cellular networks and found ways of mitigating these attacks. This was the first attempt, first recognition of this type of attacks. This work resulted in a highly successful product, 9900 Wireless Network Guardian. It has been deployed in over 20 service providers networks around the world. For example, Bell Mobility in Canada, NTT Docomo in Japan, KPN in Netherlands, and Verizon here in US. This work received a lot of attention in technical press. I gave a talk in New York City, and here is an article that appeared in Computer World. Now, all the attacks that you can launch against IP networks, they can be launched against cellular networks. These include spam, virus, bombs, malware, all attacks that you're familiar with. Now, there is another class of attacks that can be launched as these wireless networks. The reason for this vulnerability is these cellular networks have some limited resources. For example, they have limited signaling capacity, limited RF spectrum, and handsets have limited battery capacity. There's some low intensity attacks that can be launched against these networks, which can degrade performance of these networks. I'll give you some examples of these. Suppose if Verizon in, say, Baltimore uses a bunch of IP addresses. If I send messages to each one of these IP addresses reasonably frequently, it will keep all Verizon phones awake in Baltimore. And the battery life for these phones will go down from, say, a days down to a few hours. The reason for this is these phones need to go to sleep to conserve their battery. Now, if I send a bunch of short message sequences after I send these short message sequences, a tear down connection, this will saturate signaling subsystem of these networks, and it will be very difficult to set up new connections. Now, these cellular networks have circuit-rich core as a part of their signaling system. So every time you send a short message, a connection needs to be set or need to be turned down. So many application developers do not know limitations of these cellular networks. For example, there was an Android application which was used to access weather information. What the application developers did in their infinite wisdom, millions of Android phones will contact control server synchronously every 6 hours. So in red, you see some peaks. This they are every 6 hours. By the way, the x-axis here is the time. The y-axis is the traffic, the control traffic. So in red, you see this erroneous application, and in blue, you see the corrected application where these accesses have been randomized. So anytime there is a major application upgrade, it can significantly increase network load. In 2013, Facebook came up with a new update for their mobile app. This increased signaling traffic by 60%, airtime by 25%, and video volume by 350%. So every time application developers are coming up with an upgrade of their application or introducing new applications, companies like Verizon and AT&T had to be very, very careful. Any questions? Next, I'm going to talk about some projects I'm working on now. I'm working on a DARPA project for 5G networks. Here, what we want to do is we want to go from 5G specification directly to code. And there's an intermediate representation of finite state machines. So these 5G specifications are typically done in natural language, and they also have some diagrams along with. These diagrams have mostly message sequence charts. Message sequence chart basically show how different packets are exchanged between different parties. So we are converting these message sequence charts to skeletons of these finite state machines. And then we use natural language processing to put meat on this skeleton. And we are getting some fairly promising results. This work is still in early stages. Next, I'm going to talk about a very exciting project I'm doing with folks at Johns Hopkins, V2X project. Vehicle to everything communications. This project I'm doing with Tony DeBura, Khalid Halba from NIST, and Krishan Sabnani, and they are two very smart students who are working with us on this project. Now, if you look at a self-driving car, it has a bunch of sensors in it. This control unit gets information from all of these sensors and makes driving decisions based on these inputs. What if we can get additional information in these cars? For example, if we can get information from sensors in other cars or from sensors mounted along poles on a highway, the car should be able to make better driving decisions. But this requires that information gets transferred reliably and securely to the car. This information is coming from external sensors. We need to make sure that this gets done properly. So the three properties that are needed here: reliability, timely delivery, and security. Reliability needs some work on error control protocols. Timely delivery requires work on ad hoc methods and mesh networks. In fact, this is a very interesting project being done that's been done by Year on mesh. I believe that should help us. For security, one of the ideas we are just beginning to explore is, can we make this highway zero trust system? In each car, we are going to build a software-defined parameter. Maybe we can interest Avi to work with us on this project. So we believe there's a lot of interesting work that can be done in this project, and also should have tremendous impact on practice also. By the way, we believe this additional information will bring the self-driving cars close to level 5 autonomy. Any questions, comments?
Just one quick comment, since you mentioned that I might be interested in this. This is coming full circle for me. So in grad school in Michigan, they were starting to look at all kinds of vehicles. And I was actually funded in grad school by the IVHS, which was Intelligent Vehicle Highway Systems. So look forward to discussions about that. And we're talking.
Wonderful, wonderful, wonderful. Hopefully you'll join us.
Yep.
Wonderful. Now, there's been some discussion about me increasing my role at Johns Hopkins. So here are some of the things I like to do. I like to start some networking program that is synergistic with Johns Hopkins core strengths in areas like medicine, assured autonomy, and I'm sure there are many other strengths also that I'm familiar with. And there are also a lot of great programs going on. Already mentioned Year's program on SMesh and also it is seems always also interested, has some very interesting programs also. So I'm sure there are many other programs that I'm not familiar with. Another very important point I want to make is basic networking is becoming as important as programming in all domains. When I was serving an advisory board in this department, it was really impressive. Everyone in the university wanted to take programming courses there. The same thing should happen to networking also. Any system that's been worked on in Johns Hopkins, if it's not already connected to internet, if it gets connected to internet, its capabilities can be increased at least by a factor of 10. So a prepared part of my presentation is over, and I hope we have some good discussion now.
Yes, if anybody has any questions, maybe they can either raise their hand or unmute. I can see everybody on my screen. And I want to start with, so Mike, Mike, can you go ahead?
Oh, no, sorry. I was just, that's the applause reaction.
Oh,
Yeah, that was applause.
Tony, I think your hand is raised, right?
Yeah, well, first of all, Krishan, thanks for a great talk and for taking us on a sweeping tour of networking and your involvement, and also for kindly providing the update on the research that you and I did together. I appreciate that. And when you're talking about these extremely complex networks, I'm wondering if you could comment on how verification is keeping up with all of this, you know, formal and other methods such as simulation, because my impression has been that it's been a big challenge in the past, and so. And you know, you'll recall, I think it was in the 1987 or so, the AT&T network went down because of basically a protocol error that created maybe a race condition. I remember vaguely, and there was a domino effect throughout all the switches in the AT&T network that took the entire system down for a time. And so, you know, catching these kinds of errors are critically important, but at the same time, the complexity is just increasing all the time. So what's your assessment of this?
So Tony, thanks for leading me to a topic actually I wanted to discuss. So I just want to show you, I have done over the years a lot of work on formal methods. In fact, I did not get a chance to talk about that on proving correctness of protocols, applying techniques from finite state machines to protocol conversion to different version of testing. For example, I did some work on passive testing. But when I was doing this work with Tony DeBura and with others on this, the main networking community actually did not pay much attention to formal methods. So in '93, I started working on practical wireless networks, so I kind of moved away from that. But at SIGCOMM, I was really very happy to see a lot of papers on formal methods. In fact, the first paper was from Hari Balakrishnan from MIT on formal methods applied to congestion control. So it's really becoming very hard. It's because of the problem that Tony, you mentioned, these networks are becoming very complex. So the mainstream networking community, which used to work more on performance analysis, where people like Len Kleiner, Michel Schwartz, and on implementation, people like Windsurf, etc., they seem to be moving to formal methods. So this has become really very important to realize. Now, how to solve these problems? I think it will be foolish to check for correctness after these networks have been synthesized. They have to be baked in from the beginning. that means, the work, for example, what you're doing on assured autonomy, do it in a distributed fashion so that the network really does not have these problems. For example, in wireless network, there was a lot of work done in self-management, which is that when you bring in a new network element, it kind of senses the environment and somehow configures it correctly, and it will not make a mistake. And those are the types of things which will be the most important things to do in terms of this. So formal methods are really very important. Now, I'm sure that a lot of people in this audience are experts in machine learning. I have, by the way, started learning on machine learning, but I'm not an expert in that. But at some point, I'd like to start working on that. So in machine learning, bringing formal methods also will be very important. For example, if there are hard safety properties, they should be brought into these neural nets, because in a neural net, so if you just based on some data, they may not put these hard limits. And they would be very important to put in these hard limits also. So if machine learning is used in these networks, then a combination of formal methods and machine learning will be very important also. So Tony, thanks. You read my mind. And in fact, I want to lead this discussion in that direction.
It definitely wasn't planned. Well, thank you. And I also just finally wanted to comment that, for the audience, there are countless research topics that Krishan touched on in his talk. I think there's an amazing opportunity for people who are more interested, want more information on this whole area. It's tremendous.
So I have a question. I want to take you back, maybe if you can go to slide 14, because I think you touch here a very critical problem that the soft router can help, and we can see it. This can you go one slide back from that?
Okay.
Yes.
One?
Yes. So what you're showing here basically is that by using the soft router architecture, you can, in the network routing stability, you can resolve, faults. I would say maybe 2 to 3 times faster in OSPF. OSPF is giving us the routing within one network. And I can definitely believe that if you can comment a little bit about it, because the next slide here, I can see it happening in OSPF because it's one control domain of one ISP. When you talk about in this slide, in slide 14, in the BGP slide, I see the huge potential, but the problem here is that the different participants in that routing between the networks, so this is the internet routing between networks that are using BGP, here the domain is different. There are many parties, so the need for a soft router technology to work here, they need some agreement, like in the inside one network with OSPF, I can, you proved it, 3 times better, that's like huge. What do you have any comment for inside one network, and what's the difference between that and how can we make it a reality in the BGP world?
So here you brought in a very important point. There's always a battle between centralizing some of these computations and distributing them. By centralizing, oscillations can be removed. I don't know whether I'm sure you're familiar with RIP, which uses Bellman's ports, route computations. It is really very noisy. It causes a lot of, in OSPF, there's centralized computation, but it's distributed. So again, a good study on the what to distribute and what not to distribute will be kind of very important. In fact, this is a study that it should be used probably in other domains also, because this convergence can be done much faster if it is done. But then if it's centralized in only a few places, it has scalability problems, and it's difficult to react to problems. So again, I absolutely agree with you. There's a lot of important work on this. Now, BGP basically policies are based on politics, whether this company wants to talk to that company, whether they're competing with each other or not. And as a result of this, there are a lot of oscillation problems. In fact, some researchers have made it a career to, how to deal with this convergence problem. In fact, at one point, I was pushing the community to work on versions of BGP, which brings in some topology information about how well the underlying network is working. Because if you do that, then a lot of these problems can be done. So in fact, this is something that we can push in, ITF and other places to really, the time has come for that. But BGP is a very kind of a crummy protocol, as you pointed out.
So, I mean, I think, so I looked at that problem. I had to really solve it in sub-second performance about a decade and a little bit ago in the commercial world. And, you show that with OSPF within one network, you are doing it with the soft router. With BGP, the problem that we faced at that time was that these are different domains managed by different entities. So what we ended up doing was solving it at an overlay level. So it's like a programmability thing, but it's programmability at a higher level that you can really do it even if you don't have agreement or collaboration of the ISPs below. Because it looks to me that when you want to do it at BGP level, you'll need the ISPs to collaborate. Because right now, outages or that level lead to 40 seconds to minutes outages.
Right.
Just last year, the biggest ISP, CenturyLink, or what used to be called level 3, went down by exactly the same mistake you talked about and vanished from the internet, causing problems for basically 6 hours around the internet. So exactly that kind of solution that you propose could help in that, limiting an outage like that to maybe like a sub-second one. Just a thought here that.
Now, by the way, when you were speaking, I came up with an idea which you may already have. So the reason why in BGP, these operators don't want to share information with each other is, for example, Verizon does not want to share its information with AT&T, because if AT&T knows about the internal problems of Verizon, they can use it in their advertisements that, their network is crummy, we are better. So what you are saying is an overlay network. So if there is a neutral party which gets this information, but it hides it from other networks. By the way, many of these enterprises, they get services from different ISPs just to have diversity, to avoid this problem.
Yes.
So if there is a neutral kind of a third-party player, which, for example, if say somebody is going to Verizon's network and Verizon's network fails, it goes through AT&T's network, and AT&T clearly will be paid for that, but somehow AT&T cannot use that information in its advertising. That'll be very powerful, by the way. Maybe you have an idea for a new business.
Well, great. Anybody else has any other question that would like to raise with Krishan?
I do have a question about SDN.
Go ahead, Sudhe.
By the way, great talk, thank you. So I had a question about SDN that I wanted to see your take about as someone who has been involved in the earlier versions of it. So if you look at the history of networking, it is kind of interesting because it seems like that the field is going back and forth between centralized control and distributed control, right? And for example, for SDN and the recent movement to open flow, it seems like that cloud providers and data centers, they were, well, either the main force or one of the major forces of pushing the networking industry in that direction. Because of convergence and going back to Tony's point, making verification easier, right? It's much easier to verify a centralized network compared to an incredibly complex protocol like BGP. But if we look at the most recent work from the same networks, it seems like that they are kind of going back, right? Especially because of performance considerations and the limitations of BGP. So now my question is, do you see the same trend in other types of network, for example, in telco, of going back to distributed versions?
Well, there are functions that will be distributed. There are other functions that will be centralized. By the way, this going between back and forth between centralized and distributed happen even in the computing industry also. Many of you are young, but there used to be mainframes, centralized computers. Then we moved to PCs, and now we have moved to cloud computing. Now, I've been working on network for a long time. In fact, internet is fairly recent. There was a dominant networking standard used by enterprises called SNA. It was done by IBM. It was highly centralized. This was true in telecom industry also. There was X.25 and then ISDN and all of those things, ATM. There was a lot of centralization in them. Now, internet, when it started, it was ARPANET, and it was really done for defense applications. So when BBN built these SIEMs, everything was distributed. When Cisco and Juniper, they started building these routers, they wanted to control everything, which, as I showed you, which had control plane processing and packet forwarding packed in a single box. But they really do not belong in the same box. They really should be taken out. And this is what this SDN work has done, that this is a function that really should not be distributed at level. It was done for business reasons. You will see a lot of these things going back and forth between various things. In these wireless networks, I talked a lot about cellular networks. Initially, these networks were highly centralized. Then currently networks are, based on, in fact, a lot of the nodes in them are small cells, especially in, say, for example, 5G and even more in 6G. This depends on what application or which part of network you're talking about. We should use either centralized approach or we should use this distributed approach. For example, SDN approach for these core networks, small cells for increasing the overall access capacity of these wireless networks, because you get the complete spectrum in each one of these small cells. So again, I would say there's no right and wrong answer. I hope I answered your question.
Yes, you did. Thanks.
All right. Anybody else have any comments or questions? So I think we thank Krishan for a wonderful talk. We have slots to meet with him later today and some tomorrow. So I'll see you around when we see you. Thank you very much.
Yeah, thanks a lot for inviting me. I really had a wonderful time here.
Yeah,
and I look forward to all the discussions later.
Yes.